So now that you have prepared your simple linear regression model, you need to look at how well that model fits the data that you have. So the first thing that we need to talk about is our sum of squares again. So our sum of squares due to the error is going to be the measure of the error in using your estimated regression equation to predict the values of your dependent variables in a sample. So for our example Butler trucking data, we end up with a sum of squares error of 8.0288. Without any knowledge of any related variables, we would use the sample mean y bar as a predictor of travel for any given driving assignment. So to find y bar, we're going to add up all of our values of y sub I, so that would be our travel time in hours. From the table in the lower left-hand corner, we would get a value of 67. Then we would divide that by the number of observations in our data that's represented by n. And so here we have 10 observations, so we have a y bar value of 6.7. And so in this picture over here, we see our line of y equals 6.7 to represent how well we would predict the values in our Butler Trucking Company example using the average y variable. So from this figure, which again is going to highlight the residuals for driving assignments 3 and 5, we can see that our average y variable, or average travel time, tends to overpredict travel times for driving assignments that have relatively small values for our miles traveled, such as driving assignment number 5, and then it tends to underpredict the travel time for driving assignments that have relatively large values for miles traveled, such as our driving assignment number 3. So with our sum of squares total, for our Butler trucking example, we look at an individual assignment in the sample and we find the difference between that individual sample and the average to find a measure of our error that's involved when we use our average to predict any one individual observation. And when we take all of those values together and square them and then add them up, we get our total sum of squares. And so the sum of squares total is going to be a measure of how well the observations cluster around your average or y bar line. And so if we look at our data again, we now have our yi minus our y bar, and then we take that value squared to get our sum of squares total of 23.9. And then in the upper left-hand corner, we see a linear regression line that's been fit with an estimated regression of y hat equals 0.0678 x plus 1.2739. And we also see the line corresponding to y bar equals 6.7 as a dashed horizontal line. Note that the points tend to cluster more closely around our estimated regression line than they do about our horizontal line, which is our average of all of our y values. So then we have our sum of squares due to our regression. And so that's going to measure how much our y hat variables, or our predicted values, are going to, on our estimated regression line of y bar, are going to deviate. And so we have our sum of squares total is going to equal our sum of squares regression plus our sum of squares error, which is the same thing we saw before with ANOVA, where we had our sum of squares model plus our sum of squares error to give us our sum of squares total. So if we look at our Butler Trucking Company example, we have our sum of squares error from earlier in our presentation being 8.0288, and then our sum of squares total from the last slide of 23.9. So sum of squares regression is equal to sum of squares total minus sum of squares error. So 23.9 minus 8.0288 gives us a value of 15.8712. So the next statistic that we need to look at is our coefficient of determination. And that really, the formal definition is the proportion of the total variation in the dependent variable y that is explained or accounted for by the variation in the independent variable x. What this really means is this is talking about the total percentage of the sum of squares that can be explained in our outcome variable or our y variable by using the x predictor variable in our regression equation. And so basically it provides a more interpretable measure of our regression equation's ability to predict. In addition to looking at the ratio between the sum of squares regression and the sum of squares total, your coefficient of determination, r squared, is just taking your coefficient of correlation and squaring it. And so oftentimes, when you get farther away from this particular lecture, you're probably not going to call it the coefficient of determination. You're just going to be calling it r squared. And that's how it's more commonly referenced anyways. So if we look at an example with our Butler Trucking Company, we end up with an r squared value of 0.6641. And so the way we can interpret this is 66.41% of the total sum of squares can be explained by using our regression equation to predict our time on the road. And so our standard error of the estimate is a measure of our dispersion away from that line. And so it's kind of similar to what we were looking at with standard deviation. It's basically the same concept. So the standard deviation, remember, is going to measure the dispersion around a mean. The standard error of the estimate is going to measure the dispersion around our regression line for a given value of x. And so the relationship between our correlation coefficient, our coefficient of determination, and our standard error, they all kind of go together. So our correlation coefficient gets squared to become our coefficient of determination. We got that. But also, when we look at our standard error, remember that estimates how close the actual values are to our regression line. So we actually want the standard error value to be very low. And then the correlation coefficient measures the strength of the linear relationship between our two variables. Well, if we're doing a linear model, we want this to be a very high value. So typically, these two values are going to be inversely related just because of the nature of what they measure. And so, as the strength of a linear relationship between two variables increases, the correlation coefficient increases, but the standard error of the estimate is going to go down. So let's look at the regression equation slope test, right? So now that we've kind of started looking at our model, the next thing we need to do is conduct a test of hypothesis to see if the slope of the regression line is different from zero. And so if we find that the slope is different from zero, then we can conclude that using the regression equation is going to add to our ability to predict the dependent variable based on the independent variables. And so this test is going to be equivalent to the test for correlation coefficient. Here we're going to use beta to represent that population slope. So if you look at the formula, you see it's basically a t-test. We're looking at our sample value b minus 0, because we're comparing it to whether or not it's 0, divided by our standard deviation of b, or my error, my standard error of b. And so the big difference here that we're looking at in terms of a t-test is instead of using n minus 1 degrees of freedom, we are using n minus 2 degrees of freedom. So let's go to our Butler trucking example and work it all out. So our null hypothesis is going to be that b is less than or equal to 0. And our alternate hypothesis is that our slope is going to be greater than 0. We're going to use a significance level of 0.05 because that's what we normally do. And so since this is looking at whether or not it's greater than or less than 0, this is going to be considered a one-tailed test. So if we do not reject our null hypothesis, we would conclude that the slope of the regression line could be 0. Okay, So since we're just comparing two values like this, we're going to use the test statistic t from what we did before, and we're going to find the critical value from our t-table with our degrees of freedom being n minus 2, so 15 observations minus 2 gives me 13. And so with a significance level of 0.05, we have a critical value of 1.860. So when we take our parameter estimate b minus 0 and divide it by our standard error, we get a value of 3.98, which it is greater than our critical t-value. So this means that we are going to reject the null hypothesis and conclude that the slope of this line is in fact greater than 0.